Hi everyone, and welcome to Austin Organs. My name is Jake Dowgewicz. I'm the Factory Design and Sales Director. Thanks for tuning in. I look forward to showing you around the shop and some of the Austin ways of building pipe organs.
John T. Austin was born in England in 1869. He enjoyed a childhood that highlighted choral singing and amateur organ building with his father. In 1889, he immigrated to America from England, despite having all of his possessions stolen from him on the ship crossing the Atlantic. John found work at the Farrand and Vody Organ Company in Detroit, Michigan. While working for the company, he developed the soon-to-be famous universal air chest system. At a mere 23 years old, he received a U.S. patent for this innovative concept. He attempted to sell the idea and patent to Farrand and Vody, but they had little interest. John instead was able to catch the ear of Clough and Warren Company in Detroit, a reed organ manufacturer. After settling on an agreement, Clough and Warren started a new pipe organ division led by John Austin. The first Austin patented organs were built in 1893. Unfortunately, in 1898, while installing Opus 22 at the Fourth Congregational Church in Hartford, Connecticut, the Clough and Warren factory burned to the ground. After the fire, the Austin Organ Company was incorporated by John T. and his son, Basil Austin. The Austins rented space in Boston to complete two major contracts in New England, but during that year, prominent Hartford businessmen convinced John to move to Hartford. He leased space on Woodland Street in the recently built and never occupied mill buildings during the spring of 1899. A few years later, the thriving new company purchased the property. During the first few years of the new century, the company engaged in several clever but risky endeavors that placed them in the public eye. In 1900, the company secured the services of a gentleman named Robert Hope Jones, a rather controversial organ architect and tonal designer who developed some signature voices that continue to this day. In 1902, Austin sponsored the first American tour of Edwin H. Lemaire, who soon became one of the company's most ardent champions. Through constant growth, along with the reliability of the universal air chest system, the Austin Company had become nationally recognized by 1910. In 1915, Mr. Lemaire's concert season on Austin Opus 500 at the Panama Pacific Exposition commanded enormous success. He performed over 120 concerts to more than 150,000 people. The years between 1915 and 1931 were the most prosperous in Austin history. The company produced a staggering 1,200 pipe organs over that span, or approximately 75 instruments per year. However, in 1929, the Great Depression hit and sales began to dwindle. By 1935, the officials of the company ceased organ production and began liquidating company assets. In 1937, Frederick Austin and Basil Austin reorganized and reformed a newly established organ company called Austin Organs Incorporated. During World War II, the factory was contracted to produce coat hangers and glider wings for the war effort. After the war's conclusion, Austin Organs Inc. saw tremendous growth and proceeded to expand the factory several times. In 1973, his son, Don Austin, became the president of the company. He remained president until 1998 when Kimberly Austin assumed that role, but remained CEO until his death in 2004. A year later, Austin Organs Incorporated was purchased by Michael Fazio and Richard Taylor. Under Michael's and Richard's watchful and innovative eyes, this well-established firm has entered its second century of pipe organ creation. Austin Organs Incorporated continues to innovate, inspire, and create instruments that endure the test of time. Quoting a byline from our centennial celebration, we remain proud of our past and focused on our future.
Hi, my name is Mike Fazio. I've had the honor and responsibility of being president of Austin Organs for the past 15 years. Also in my role, I'm the tonal director for the company. In that time, we've had the opportunity to not only expand our offerings and improve the company from its previous administration, but we have been able to change our musical language here at Austin. We've adopted some time-honored tonal traditions and incorporated them into a new wave that's reaching out to new instruments across the country. And we hope that you can experience some of that with us today.
And here we have Floyd Higgins, the senior design engineer. Hello, Floyd.
Hey, Jake.
Floyd, I was hoping you could tell us a little bit about what you're working on, what you're doing.
Sure. Well, my job began when we took the old organ out. I went about measuring all of the pipe work and also measuring the spaces. And then Mike Fazio, our tonal director, came up with a detailed stop list explaining how all the pipe work is being used. And then I came up with a drawing. And we use the computer to, in a sense, model what the new organ will look like. So I can put all of the elements in place and make sure that they're all going to fit and that they can be easily accessed. And once the model is complete, then we translate that over into what we call a shop drawing, which is what we will use to actually build the organ. And then, of course, we print it out with these drawings. And then doing this process allows me to put together what we call a lumber bill. And the lumber bill details every component of the organ, which there are many thousands. The type of wood, the dimensions, and these are instructions for our lumber mill to cut up all of the lumber, and then we begin to assemble. So right now, the design of the organ is 90% complete, and we are putting it into production.
Great. Thanks, Floyd.
A lot of the modeling for the structures of the chest of the organ itself was, of course, done on the computer, and you can see here some of the pipes were laid out using the computer. But at a certain point, we like to also use the old-fashioned system that we've used for many years here at Austin, which uses all of these discs. And what we can do is we know that the spacings of notes, let's say low C to low C sharp, or low C to D if it's a chromatic chest or an M chest, we know what those spacings are. So these bars help us to line out the spacings of different configurations of stops. So this might be a 2-foot stop, and then a 4-foot, and then this is a wooden gedect. So we know that this can't have a conflict there, so we place it there, and then we place this one here. Here's an 8-foot stop, for example. Keep some space there, line it up that way. And then wherever these line up, we mark them on the stick, and then the stick, with a few extra indications, we can take it down to the chest shop and they will build the chest. And then, of course, an important part of our archives here is that we keep all of the sticks that we built. Here is a set of sticks from 1952. We've brought them out because we have a project where they want to make some modifications, and we know exactly how those chests were built many years ago.
As we come up onto the 3rd floor, this is the floor that we say really all the action is, because this is where we make all of our own actions. All of the Austin pneumatic components are made in-house here, and basically they start with the Austin magnet. We wind our own magnets here, so essentially we have this nickel core that is heat treated and powder coated. Those are then set inside of this machine here. It winds 2 magnets at a time, and there is this copper wire that gets wound around, and there's a coating on that wire, and that coating essentially melts as it's wound around, as there's alcohol that drips down, rubbing alcohol that drips down onto the magnet. When that alcohol evaporates, the coating solidifies, making one solid magnet. It comes out in through a series of bending. We end up with this horseshoe shape that fits onto the pneumatics. All right, from there, we obviously need something to attach the magnet to. This is what we call the magnet block machine. So there's this block of wood that the magnet gets attached to. This comes up as basically we make cards of this this wooden block here, and they all get cut to size. This guy here is going to get set into this machine, similar to that. And at that point, there's this, it gets held in here and through a series of drill bits, down from the bottom and again up from the top and then in through the side. We end up with a part that looks like this. It's about the same, except now there's all these holes drilled in it. These are between wire slots on the sides here that the terminals for the magnet get attached to the armature seat holes and exhaust holes and so on and so forth. All right, here we have an Austin pneumatic set up on the test bench. What this does is it simulates being inside of the wind chest. The system works on a pressure differential. So essentially what happens here is we would be inside of the organ chest, and what we would do is we'd play the note, and through a series of diversion of wind pressure, this action will play. So all we're going to do is we're going to put 12 volts to this magnet here, and you can see what's going to happen. There we go. Oh, one-handed. You can see how fast actually that system is. Obviously, before anything gets sent out, everything is fully tested. This one looks good. In one corner of the shop, we have this demonstrator that we bring to conventions, so on and so forth. Basically, this is a small chunk of the universal wind chest that we have running on vacuum to simulate being inside of the pressurized air chest. Along the front, you can see the manual motors, one per each key, and on the right side, we've got the stop actions. Here we're going to turn the stop on. This will be the gedect. So this turns the stop action on, which rotates this roller, acts as a pivot point to the pipe bar jack. In this case, the pipes are split onto 2 bars, and play up and down the keys, making the manual motors play. You can see as they collapse, they pull that tracker, which is connected to a pipe bar valve. You can see the system is very fast. If it's all in good operating condition, it's impossible to outplay. And as we graduate up, the pipes get smaller, require a smaller valve, therefore a smaller pneumatic to pull it across the chest. Alright, well, before any organ leaves the Austin Organ shop, it is fully set up
almost to playing condition. We don't put wind to it. We don't obviously secure anything to the ground, but in this room, this is our erecting room. We've got it's about a 30-foot ceiling with a crane and so on and so forth, and we set up every pipe organ we build. This is a division. This is going to be a gallery division and a solo division, aka the chest we just saw in the other room. For a church in Summit, New Jersey. These are two regulators that we have just finished building. These sit in the side of the chest, and those get connected to a valve that goes where the wind line comes in. As the organ comes up to pressure, the wind pressure pushes on these regulators. These move up and down. They'll be against the wall here, or against that wall. And what that does is it'll close down essentially a butterfly valve inside of the wind line. And so at this point, the organ maintains constant pressure no matter what's being played and what's going on. So at this point, we have all this volume of wind that's inside of these walls, and a big regulator that will keep up with the demand. So you can pull on every single stop and play every single pipe in any of these divisions, and or all at once. And our goal is to not have any drop in wind pressure, that the organ blower and everything needs to be able to keep up with it. This is one of those unique Austin designs of having this walk-in wind chest. This is the air box part of the wind chest. Again, the wind chests are next door, and essentially the chest will sit on top of here, pipes, and then up there'll be the enclosures. The enclosures have already been built for this organ. They're sitting on this cart here. And these enclosures is what contains the sound. So if we want the organ to be louder, there are these essentially Venetian blinds that open and close. And at that point, lets the sound out into the church or keeps it contained within its enclosure. In the metal making section of the factory, lead and tin ingots mixed together at a temperature of 750 degrees in the kiln. We add a bit of wax to the mixture to remove impurities. And this firing process is called flashing.
The wax interacts with the metal and brings all the impurities that are left in the metal to the top.
We skim off the impurities and move it into a trough. The metal is cooled then to 450 degrees, and we run it down a stone table covered in linen. The sheet solidifies, and the lead and tin begin to separate, but don't get too far. This is where spotted metal gets its name. From there, we load it onto a planer after allowing the metal to sit for about 2 months to reduce springiness, and we mill the metal down to its given thickness. The bigger the pipe is, the thicker the metal is going to have to be to support the weight. From there, we've got our patterns and measuring sticks that we cut out the metal to the given shape and size of each pipe and aspect of the pipe, and then it is all soldered together. From there, it goes up to a voicer like Dan Kingman, for example, where he gives the organ pipe its voice.
The metal has to vibrate to a certain extent sympathetically with the tone that's being generated by the wind blowing through the pipe. The tin-lead composition has the advantage of being soft enough for the voicer to manipulate, to cut, to pare the metal away, to adjust. Soft enough for that, but strong enough and responsive enough to make for good sounds.
The smallest adjustment at the mouth of the pipe will change the sound or the character of the pipe. Here we are nicking the mouth of the pipe a bit. We're going to open up the toe a little bit to make the pipe a little bit louder, get a little bit more air into the pipe, and make it speak a little bit more prompt.
It's now speaking right, it's a little soft. So we'll make it a little bit louder.
The pipes on the back of the voicing machine are permanently tuned. It gives us a reference pitch. Tuning and voicing are kind of go hand in hand. I'm going to trim the pipe a little bit. There's a little over length. Attach the tuner.
I activate that pipe and listen to it with the one in the front and listen for beats to see if they're in or out of tune. And that is roughly voiced.
So you've seen the mill where we make all the chests and all of the wooden components that go into a pipe organ. Come on with me, let's go into a voicing room and I'll show you how an English horn works. Hey, welcome back. Well, I promised you an English horn, and that's what we have here. This is a vintage 1920s English horn that we're restoring for a client. It's going into a gallery division of an organ. It will be enclosed and expressive. And for that reason, we've made it a little more treble ascendant than normal. So it grows as it goes up the scale. And this gives you a little more strength as a chorus voice, a little more point. Normally, in a symphony orchestra, the English horn is really gentle and soft. But through the shades and far away, I think it'll convey that nicely. The English horn really isn't English. It was probably developed in Silesia. It doesn't resemble a horn in any way. Unlike its counterpart, the French horn, which traces its history back to the hunting horns in Germany, so it's not French either. Next to it we have the flugelhorn. I have no idea what a flugel is, but we oftentimes will use a flugelhorn in an instrument as a great chorus voice on the great organ. So in comparison, we have the French horn, which has got lots of color and a great solo voice. We have the flugelhorn, which makes a nice chorus voice. And conservatively, the English horn as well. So you see a nice dynamic difference and color difference between all three. Over here we have, of course, the clarinet. This one is a little bit larger than you might be used to. It's being voiced as a basset horn in an exposed division. And next to it, we have the Rochelmai, which really traces its roots to the Baroque instruments. At 4-foot pitch, it makes a nice color stop. And finally, let us not forget the trumpet, because an organ just isn't an organ unless it has trumpets in it. That's not a trumpet. Flugels get into everything. And that's a trumpet. Voicing reeds is completely different from voicing flues, and I won't bore you with that, but if you'd like to see, come by Austin anytime and we'll be glad to show you.